Hi guys, welcome back, I suppose. So today we are doing May June 2017 paper 119701 chemistry. So let's start with question number one. Which molecule contains six bonding electrons? Okay. So first we have C2H4, which is basically ethene, right? So let me draw it out. Okay. So how many bonds are there? There's one, two, three, four, five, six. Six bonds, right? So in each bond there are two electrons involved. One like the two electrons involved. So then six times two is going to be 12, which means in ethene we have 12 bonding electrons. Okay. Then in H2S you have yeah, and then obviously there are two lone pairs on sulfur, but they're not really talking about the lone pairs, but just the bonding electrons, right? So one to two bonds, two times two is four, so that means again there are four bonding electrons. And then NCl3 is something like that. I'm just drawing rough diagrams, okay, not the ones with wedges and stuff. But yeah. So NCl3 there are three bonds, one, two, three. So three times two is going to be six, which means yeah, it has six bonding electrons. So C is probably going to be the answer. SF6, you can immediately see that because there are six fluorines, then that means there are six bonds, right? Six bonds means six times two is 12. So there are 12 bonding electrons, which means again it's not going to be the correct answer. So then yeah, the answer is going to be C and Cl3. Okay. Next question. The mass spectrum of a sample of lithium shows that it contains two isotopes, 6Li and 7Li. The isotopic abundances are shown in the table. What is the relative atomic mass of this sample of lithium given to three significant figures? Okay, so we're just going to calculate it. 7.42 plus 92.58 is 100%. You just check it, I mean, usually it is going to be 100%, but it's always best to confirm if the sum of the isotopic abundances that they've given you is 100%, okay? Or 100, if it's relative abundance. Anyways, so calculation is just going to be 7.42, which is the first one, which, yeah, that doesn't take 4. 7.42 times 6, which is the mass number, plus 92.58 times 7, and then divided by the total isotopic abundance, right? So that is going to be 6 plus 92.58 times 7 divided by 100. Okay, it's going to be 6.9258. And they asked you to give it to three significant figures, right? So that's going to be 6.93, which is option D. So that's going to be the answer. And next question. A sports medal has a total surface area of 115 centimeters squared. It was evenly coated with silver by electrolysis. That's cool. Its mass increased by 0.216 grams. How many atoms of silver were deposited per square centimeter on the surface of the metal? Okay, so silver, right? So if you look at the periodic table, where is silver? Silver, yeah, 107.9. That's a smaller mass, so 107.9. So if we want to find, well, that's 107.9. So what can I do? I can do one thing, which is because they're asking about atoms per centimeter square, right? So what I can do is I will use this mass. Like basically, we know that moles are basically mass over the relative atomic mass, right, or the molar mass. So I will find the moles and then use the moles to find the number of atoms, which is like the number of atoms equal to 0.216 grams, and then I will just use what do you call it, the cross multiplication method. I mean, you see what I'll do. Okay, so 0.216 and then divide that by 107.9, which you got from the periodic table, and that will be um, 0.00200185. Well, then it's going to use a calculator value, okay. Or you could say it as 2.00185 in 10 to the power minus 3 moles. Anyways, now we know that like moles, basically, wait, wait, what's this? So the number of atoms we have, which I can denote as a big N. So that is basically the number of moles times Avogadro's constant, which I'll just stick as L, okay? So this is Avogadro's constant, that's the number of moles, and then that's the number of atoms you have. So if I want to find the number of atoms, that's just going to be the number of moles I have, which is 0.002001. If I just use the calculator value, okay, times Avogadro's constant, which is 6.022 into 10 to the power of 23. Okay, so just do this calculation, and you get 1.14, wait, 1.2055162 into 10 to the power of 21 atoms. Okay, so now what I know is that so basically the total surface area of the metal was 150 centimeters square, right? And it was evenly coated with silver by electrolysis, and its mass increased by 0.216 grams, right? So basically, um, the whole 150 centimeters square got coated with 0.216 grams of silver, which is basically the same as 1.2055 into 10 to the power of 21 atoms of silver. Okay, so I'm just going to write that down, 1.205516. So just take the calculator value again, into 10 to the power of 21 atoms. And this is for 150 centimeters square, right? And now they're asking about the number of atoms of silver per centimeter square. Per centimeter square means you have like how many atoms of silver are there, or like per like on 1 centimeter square of the surface of the metal, right? So on each square centimeter. So now we're going to do this calculation and just cross multiply, so you get 1.2055162 into 10 to the power of 21 divided by 150, right? That's the calculation you're supposed to do. Cross multiply, and I get, okay, where should I write? So let me write it here. Okay, 8.03677 into 10 to the power of 18 atoms. Okay, is that an option? That is an option. So it's approximately 8.0 to 10 to the power of 18, correct? With two significant figures, right? So that is option A, 8.0 into 10 to the power of 18. Yeah. So that's going to be the answer. I'm going to erase this to make space for the next question. Wait, that doesn't actually need that much space, does it? Because they're just asking, what do you call it? I don't know what it's like a factual question, I suppose, or a calculation one. Which property of an atom does not affect its first ionization energy? Okay, so the atomic radius definitely does affect the ionization energy, right? Like if the atomic radius increases, then that means that the ionization energy will decrease. It's first ionization energy. The number of electron shells. Again, if the number of electron shells is increasing, that means the atomic radius is increasing. And it also means that the shielding effect on the valence electrons will increase, right? Because the number of shielding electrons increases, there are more inner shells, a greater number of shells. Yeah. So all of that means again that the ionization energy will decrease because the nuclear force of attraction of the valence electrons decreases, right? Number of neutrons, yeah, that doesn't really affect the first ionization energy, whereas the number of protons, which is the next option, that does affect the ionization energy because protons are charged, you know, um, particles in the nucleus. So then, you know, protons are what cause the nuclear charge or nuclear force of attraction on the valence electrons, right? So the neutrons, like if the number of photons increases, then the first ionization energy increases because the nuclear force of attraction on the valence electrons increases, right? On the outermost protons, valence electrons, is first ionization energy that we're talking about. But then neutrons, they don't affect the first ionization energy, right? Or really any ionization energy. Anyways, so yeah, the answer is going to be the number of neutrons, I suppose. Out of these three options, that's the four options, that's the most correct. Which molecule has the largest overall dipole? Okay, so first one, there's not a very large electronegativity difference between C, H, or obviously there's not any electronegativity difference between C and C. Suppose you could think about the different environments. Basically, this molecule does not already have such a great dipole or any dipole I can see at least. So yeah, we can cancel out option A, and similarly we can cancel out option D as well because CCl will have a dipole, and um, the electrons will pull towards Cl because chlorine is partially negative, carbon is partially positive. That's the dipole that's created. Even here, that's dipole that's created. But then, so then, this, it's kind of like vectors in mechanics. If you've studied maths, so one is going to be pulled there, the other dipole is in that direction. So, they basically cancel out, right? So, and whereas like C and C don't have a big difference in their electronegativity, so there won't be a significant dipole between these two carbons, right? But then again, this molecule does not really have a dipole. Okay, symmetrical molecule as well, so these two will be equal um dipole moments. Anyways, now it's between B and C. So B, you have this oxygen and this partially negative oxygen, partially positive carbon. And the five most electronegative elements are fluorine, oxygen, nitrogen, chlorine, bromine, or NClBr, right? So you have oxygen, chlorine have a good, like a great electronegativity difference, right? So it will be a dipole moment. And then C and C don't have much of a electronegativity, like, obviously because they're both the same atom, right? C, carbon, and carbon. Okay, anyways, here you have partially negative oxygen, partially positive carbon, as well as partially negative fluorine here and partially negative chlorine. So one is being pulled here, and this is going like this, and this is going like that. So again, it's basically, you know, vectors, I suppose. So it's like this. You can resolve this, and then these two you can say that they cancel out. But then over here you have this one and this one, right? So again, these are opposing the dipole moment caused by this oxygen. So in essence, basically, like, because of the electronegative chlorines as well, because they're like there's a highly electronegative oxygen as well as two electronegative chlorines. So because of that, the overall dipole moment gets reduced. Actually, these two cancel out firstly, and then I'll use another highlighter color. So these two oppose the dipole moment of this oxygen, you know, uh, between the oxygen and chlorine. So then the overall dipole basically gets reduced, and they ask for the largest overall dipole. So over here in option B, so you can cancel out basically A, C, and D, and so the answer is going to be B, because this of like there's no opposing, like there are no other dipole moments. It's just between like CO. So and that one is just this arrow that I've shown here. So it has the greatest overall dipole. That's not cancelled by any other dipoles because there's not really a great dipole moment between C, right? So yeah, hopefully that makes sense. The answer is going to be B. Okay, next question. The complete combustion of 2 moles of a straight chain alkane, okay, that's, yeah, 2 moles, produces 400 cubic decimeters of carbon dioxide measured at 301 kelvins and 1 in 25 pascals. Carbon dioxide can be assumed to behave as an ideal gas under these conditions. Okay, so they're saying it can be assumed to be an ideal gas. Ideal gas, that always brings the equation P equals nRT into our minds, right? So that. Now, what is the formula of the straight chain alkane? Okay, so if I just write down a rough formula, we can say CnH2n plus 2. That's the formula for an alkane generally, right? Like, for example, C2H6 or C3H8. So that's CnH2n plus 2 is the general formula for an alkane. And then it's being combusted, right? So I can say plus O2, and then that is giving you CO2 and H2O, because that's the combustion products. And so if there's n mole, like Cn, that means we have n moles of CO2, and then H2O will be 2n plus 2, right? And then O2 will be, so there's 2n over here, and then over here you have 2n plus 2. So then 2n plus 2 would be, I suppose. Wait a second, did I do something wrong? Yeah, I did do something wrong. Look, wait. because here we have 2n plus 2 h, right? And here we have h2 already. So basically, I have to do 2n plus 2 divided by 2, which is just going to be n plus 1, right? We have n plus 1 moles of H2O actually. Yeah, sorry about that. But anyways, oxygen will then be 2n here, and then plus from this one we get n plus 1. So it's going to be 3n plus 1 moles of O2. So 3n plus 1 moles of O, in fact, and then O2 will be 3n plus 1 divided by 2. Anyways, you don't need that. I don't know why I went into that tangent. If I did a mistake, tell me in the comments. But anyways, I'm going to erase this. What is basically first what I can do is that we already know like carbon dioxide 400 cubic decimeters, 301 kelvins, and 1 into 10 to the power 5 pascals. So I can calculate using PV equals nRT or the moles of carbon dioxide PV over RT, and that's going to be pressure is 1 into 10 to the power 5. Just going to say 10 to the power 5. Volume is 400 cubic decimeters. We have to convert it into meters cubed, so multiply by 10 to the power minus 3. Okay, basically 1 meter equals to 10 decimeter because deci means 10, and then obviously that means that 1 decimeter equals 1 over 10 meters, or you could say 1 decimeter equals 10 to the power of minus 1 meters, and then 1 that means 1 dm cubed equals to 10 to the power of minus 1 cubed meters cubed. So 1 dm cubed equals to 10 to the power of minus 3 meters cubed. Okay, so that's basically why we multiply by 10 to the power of minus 3 to convert from cubic decimeters to cubic meters. Anyways, R is 8.31. Is the what do you call it? Ideal gas concentration. Yeah, so then temperature is 101 kelvins. It's already in kelvins, so that's a good thing. And now we do the calculation. Let's do it, and you should get. Okay, I got. I don't know why I write random stuff on the side. That should. It takes time to erase it. Then this is 15.99162, which is basically I can just approximate it to 16 moles, which is much simpler. So this is 16 moles. One thing to realize is that they said 2 moles of a straight chain alkane, right? So this equation that I wrote is considering this to be 1 mole. So if I got 16 moles of carbon dioxide, then basically, whatever I calculated, like if I multiply this equation by 2, right? So then I would get 2 moles of CN H2N plus 2 because I've been given. I'm basically trying to find the ratio between alkane and carbon dioxide, so I'm just taking those two. Okay, so 2 CN H2N plus 2, and then this is the ratio symbol, and then multiplying by 2, right? So this will become 2N moles of CO2. Okay, so what I'm trying to say then is that because I got this calculation for carbon dioxide as 16 moles, that means 2N equals to 16. So then n equals 16 by 2. Okay, so that's 8. So basically my value of n is 8. Okay, so it's 16 divided by 2 because they're talking about the complete combustion of 2 moles of a straight chain alkane, not 1 mole. So that's why you have to divide 16 moles of carbon dioxide by 2. And then that means if 2n is 16 by 2, which is 8, then basically now I got the value of n, right? So n is 8. Okay, so 2n is 16, n is 8, and the number of moles of carbon, Cn, H2n plus 2, right? So n 8 means it's basically C8 H2 8 plus 2, which is going to be C8 H18, right? 16 plus 2, 18. So that matches with option A already. So basically, A is going to be the answer. Okay. So yeah, because n is 8. So that's right. So A is going to be the answer. Okay. Hope that makes sense. Okay, next question. Which expression gives the standard enthalpy change of combustion of methane? Okay. So the standard enthalpy change of combustion, if you need the definition of that, is that it's the enthalpy change under standard conditions when 1 mole of a substance burns in excess of oxygen to form various combustion products, right? So let me write down the equation first. So we can say that it is CH4 plus O2 and it's excess of oxygen. Okay, so anyways, it's one mole of CH4. Okay, 1 mole of the substance, which is CH4, and then we get combustion products as CO2 and H2O. Okay, So now let me balance this. So this would be HCH4, right? It's from 2H2O, 1 CO2, 1 CH4, 1 CH2, CO2. And then it's how many oxygen atoms we have? We have 2 plus 2 plus 4. So 4 oxygen atoms, and now we have O2, so 4 by 2 is 2. So 2O2, and now it is balanced. We could write the state symbols as well if you want. Uh, it's gas, right? Liquid, gas, gas. So then make it a S cycle. So we could have the you know, uh, elements here. So oxygen, 2O2, gaseous, and then H2 is the other element here, right? So 2H2 gaseous. Okay. And then we draw arrows here for the anticipated formation of CH4 and CO2 and H2O, right? 2H2. So then, um, what? So this is basically the enthalpy change of formation. This arrow is for the enthalpy change of formation of CH4. Obviously, you don't have a enthalpy change of formation of 2O2 gas from 2O2 gas. That's quite pointless, right? And then this arrow is for enthalpy change of formation of CO2 plus 2 times the enthalpy change of formation of H2O multiplied by 2 because 2 moles of water are being formed, right? And now we have to find out what is the standard percentage of combustion of methane, which is this arrow, right? This arrow here, and I'm just going to label it as X. Okay, so basically this is a Hess cycle that I do, and this is route one. So start to end, we have to have the same start to end for the other routes. This is route one, and then the second one is like this. It's very cluttered. You don't really need to draw it so detailed during the exam, but anyways, I'm just doing it for explanation. So over here we are going against the arrow, right? So x equals to, now both the routes are equal to each other, right? So x equals to uh, over here we're going against the direction of the arrow, so we need to put a minus sign. So minus enthalpy change of formation of CH4. Okay, and then here this way we're going with the direction of the arrow, right? So don't put a minus sign, it just stays plus enthalpy change of formation of CO2, and then plus 2 times the enthalpy change of formation of H2, right? So now which option matches with what I got? Okay, so enthalpy change of formation. This one is positive. We got minus enthalpy change of formation of CH4. So we can cancel that out already. This one is where we can already cancel out. Here they put plus enthalpy change of formation of CH4 again. Here they have minus enthalpy change of formation of CH4. So I would say all the other options are immediately wrong, right? Let me just confirm with other products. So plus enthalpy change of formation of CO2 plus 2 times the enthalpy change of formation of H2. Okay. So yeah, D seems to be the correct answer. Okay. Next question. I use a different color. Purple. Solutions containing chlorate 1 ions are used as household bleaches and disinfectants. The solutions decompose on heating as shown. Okay, so they gave us this equation. Which oxidation state is shown by chlorine in each of these 3 ions? Okay. So in this ion, Cl minus, oxygen, it has a fixed oxidation state of -2. The more electronegative element is given preferential, so oxygen in the preference -2. And then plus chlorine, we just maybe take it as X. We don't know its oxidation state yet. That's fine. The whole ion has its charge as -1. So overall oxidation state is -1. So X equals -1 plus 2. So X equals +1. So here Cl has an oxidation number of +1. Okay. Next we have ClO3 minus, where we have 3 oxygen atoms, so 3 times -2, and then we don't know chlorine again, so plus X, and then the overall charge of the ion -1. So -1, then -1 plus 6 equals to X, so X equals to +5. So here Cl has an oxidation number of +5 oxygen state. Okay, or 5 plus 5 plus. Anyways, here it's directly -1, right? Because it's just Cl minus, so obviously the charge of the ion is going to be this oxidation number, -1. And now which option matches with this? +1, +5, -1. That's option C. So C is going to be the answer. Question number 9. When K2MnO4 is dissolved in water, the following reaction occurs. What are the values of A and C in the balanced chemical equation? So 2MnO4, 2 minus, that's what they're saying, plus BH2O, which we don't know the value of, gives you CMnO4 minus just 1, MnO4 minus, plus, this is basically what you call it as trial and error method, or just trying the options. Or you could try to calculate it out yourself as well. Not calculate, but use three docs things to find out. Yeah. So now OH is left to us and OH minus. Okay. So if this is 2 Mn over minus 1 Mn is here, the other Mn must be here. So this is 1 MnO2. And then what do we have? Okay. So 2 fours are 8. Okay, so this one F4 oxygen 0. So 2 twos are, so this will be minus 4 charge on this side, right? The overall charge of reactants is minus 4. Here from this we have minus 1. And if this is minus 1, then this must be minus 3 to make it also minus 4. And so the charge, overall charge will balance on both sides. So that makes it balanced in that sense. So we're going to make this 3 basically. This will be 3. This is balanced. Now we just have this H2O left to balance. Okay. So the charges are now balanced. Now we just need to balance the oxygens and the hydrogens, right? So 3OH minus. So 4, 5, 6, 7, 8, 9. So 9 oxygen atoms on this side. Let me just count again 4, 5, 6, 7, 8, 9. Yeah, 9. And then over here, 4 twos are 8. So 8, and that means we need one more here. So this should be 1 H2O. But then here we have 3 OH minus, and here we just have 2. On the reactant side, we have 2 H atoms, and on the product side, we have 3 H atoms, which means this is not able to be balanced, right? So that means we can cancel out option A because it is not a balanced equation. So yeah, we just cross this out, strike this out. Yeah. And we're going to try option B now. 3 MnO4 2 minus plus H2O, which is, we don't know it yet. Okay. Gives you MnO4 minus, C, the value of C is 2. 2 NO4 minus plus D MnO2, so it's just MnO2 plus OH minus, which again we don't know the number of moles of it yet, we don't know the value of D. Okay, so now we have 3 Mn here, 2 Mn is here, which means one of the manganese atoms must be here. So this one must be, the value of MnO2 must be 1 mole. And then now Mn is balanced. Now we have to see the charge. So on the left side, the total charge is 3 times 2, which is 6. So 6 minus. And that means on the right side as well, it must be minus 6 or 6 minus. Minus 6 is easier. So minus 6 equals to, over here, we have 2 moles of MnO4 minus, right? So 2 times minus 1 will be minus 2. So minus 2 from MnO4 minus. Then OH minus has a charge of minus 1. So plus N times minus 1. So what's the value of N? Like how many moles of OH minus N equals to? So minus 6 plus 2 is equals to minus N. So minus 4 equals minus N. So N equals to 4 basically, right? So you have to have 4 OH minus, okay? So this side is balanced. Like everyone can sort of put the find the values of D and E. Okay, now we have to find the value of B. And now the charges are balanced, right? Like minus 6 on this side, minus 6 on that side, right? Minus 4, minus 2 will become minus 6. Okay, so minus 6, that's charges are balanced. Now we have to balance the oxygens and the hydrogens again. So this is 4. 4 plus 2 plus I'm balancing the oxygens. 4 2s are 8, so 8. And then that becomes 16, right? Let me just check this again. 8 plus 4 is 12, sorry, 14. Yeah, silly mistake. 14. So this is 14. Now over here we have 3 4s are 12. 12 plus x equals to 14. So obviously x is equals to 14 minus 12, which is 2, right? So this is 2. Value of H2O, like value of B is going to be 2. So if this is 2, let's check if the hydrogens are balanced. 2 2s are 4. And here we have 4. So the charges are balanced and all the atoms are balanced as well, which means this seems to be the right answer, okay? So I would say that B is the right answer, but again, it doesn't, I mean, obviously during the paper you don't really have time, so you wouldn't go through all the options if you've already found the correct answer. But you can basically use the same method to check option C and option D. Okay, so basically write down the things and then you balance the charges first, then you balance the, we find the number of, because now we know the values of C, D, and E, so then find the number of, for example, atoms of oxygen. Then using that, you find out the value of B, and then you find whether you determine whether the H atoms will be balanced as well. And depending on whether you know the atoms on both sides can be balanced or not, you will see if the equations are right or not. Okay, but since I got the correct answers B, I won't bother doing that, but you could check those on your site again on your own, or you could use the redox method as well, like balancing it using redox equation. The same charging and stuff. Oxidation numbers. I mean, yeah, oxidation numbers. Anyways, question number 10. Methanol can be produced from hydrogen and carbon monoxide. What is the expression for Kp for this reaction? Okay, so Kp equals to the partial pressure of the products firstly, so CH3OH, CH3OH divided by the partial pressure of H2 squared plus 2 moles, right? So then that's P squared H2 times partial pressure of CO, just 1 mole, so it should be CO. Okay. Now, which option matches with what I got? If they put these products, the reactants on the numerator, which is wrong, so A and B are out. C and D could be right, but then if you look at the bottom part, that it's 2pH2 squared for some reason. For some reason, which I don't know what the reason is, because it's wrong, I guess, but like, why? Anyways, that is not the answer, basically, and so C is going to be the answer, which matches this, right? So it's PCH3OH over P square H2, or PH2, these brackets squared, times PCO. Okay, so next question number 11. When 4 grams of powdered calcium carbonate Mr equals 100 were added to 100 cubic centimeters of 0.10 mole per cubic decimeter hydrochloric acid, the volume of carbon dioxide produced was recorded. Okay, so they give you a table. Which row gives the correct explanations about these results? I don't know why I wrote table. Anyways, why the rate of the reaction changes with time? Okay, the first thing I just find out. Okay, why the rate of the reaction changes with time? Fewer collisions between reacting molecules occur, or more collisions between reaction molecules occur. Obviously, as the reaction progresses, your reactants, that's the point of the reaction, right? Like your reactants start changing into your products, which means the concentrations of the reactants start to decrease. Since there are less reactants now, so there will be fewer collisions, right? The frequency of the collisions will decrease because there are less reactants, which means obviously why the rate of the reaction changes with time, the rate of the reaction basically will decrease with time, and why? Because there are fewer collisions between the reactant molecules, right? So we can eliminate option C and D now. Okay, then why the reaction stops. The calcium carbonate is used up, or the the hydrochloric acid is used up. So for that, we just need to find out which is the limiting factor, right? So the limiting factor will be used up faster, which means when when the limiting reagent finishes, then the reaction stops, right? So this is the limiting one, is not in excess. So 4 grams of powdered calcium carbonate, so N equals M over MR, or molar mass, or mass, so molar mass, right? Or molecular mass in this case includes calcium molecular ion formula mass. Anyways, the point is fine. I just like to call things molar mass, it just makes things easier. Unless they ask me for definitions, of course. Anyways, this is going to be 0.0400 moles, okay, of CaCO3. And HCl, that is Cv. So that's going to be 0.10 into 100 into 10 to the power of minus 3. Okay, so that is going to be 0.0100 moles. Okay, 0.01 versus 0.04. Obviously, 0.04 is a bigger number than 0.01, which means that the calcium carbonate is in excess, and the HCl is your limiting factor or limiting reagent. Okay, So since HCl is um, the limiting reagent, that means it's going to be used up faster, and when it gets used up, the reaction stops, which means why the reaction stops? That the reason is because the hydrochloric acid is used up, not the calcium carbonate, because the calcium carbonate is an excess. And so where do you have two ticks? You have two ticks on B, so B is going to be the answer. Okay, so yeah, next question. Why is the second ionization energy of sodium larger than the second ionization energy of magnesium? Okay, so sodium. So basically, the second ionization energy means you're losing an electron from Na plus and from Mg plus, right? So they've already lost one electron. Sodium is in group one, whereas magnesium is in group two, right? Sodium has two electrons in its sorry, sodium has one electron in its valence shell, and magnesium has two electrons in its valence shell, right? So basically, the in second ionization energy, the second electron will be lost. You know, like the electron from Na plus will be lost from the inner shell, right? Whereas Mg plus it's still going to be lost from the outermost shell, the same shell it was lost from in just Mg, like for the first ionization energy basically. So what are the options? The attraction between the nucleus and the outer electron is greater in Na plus than in Mg plus. Yeah, that's right, because they're already stating in the question why is the second ionization energy of sodium larger than the second ionization energy of magnesium? And obviously, as I told you, like they're in period three, right? So that means there are three shells in Na plus and Mg plus. So you can just draw it out a bit. Okay. So imagine this is sodium, and then it has this one electron in its valence shell. Okay, very badly drawn, but you get the point, right? And then magnesium, it has two electrons, right? So then when magnesium loses the first electron, and sodium loses the second, third, also the first electron for the first ionization energy, right? So now sodium only has two shells left, which means like not two shells left, but like two shells with electrons basically. And magnesium is still going to lose an electron for the second ionization energy, going to lose from the same shell that it lost the first one from, but sodium loses an electron from an inner shell, which means obviously there's greater nuclear force of attraction on the now outermost electron of sodium, right? Whereas, yeah, so that's basically, yeah, obviously the attraction could be greater in Na plus, the nuclear force of attraction on the valence electron, right? So then, the second electron, I mean, the second outermost. Anyways, I talk too much sometimes using these videos, but not really. Anyways, the nuclear charge of Na plus is greater than that of Mg plus. No, it isn't, because the nuclear charge depends on the proton number, right? And sodium, it has 11 protons, magnesium has 12 protons. So obviously, sodium have a like less nuclear charge than magnesium, right? That's obviously going to be wrong. Then the outer electron of Na plus is more shielded than the outer electron of Mg plus. That's wrong, because sodium, Na plus. I mean, now this is Na plus and Mg plus, right? So Na plus has only two shells, whereas Mg plus has three shells. So obviously, Na plus has greater, smaller number of shielding electrons, right? Like it's got smaller number of shielding electrons, whereas Mg plus, because it has a greater number of shells, it has a greater number of shielding electrons. And the outer electrons, that's wrong. The outer electron of Na is in the same orbital as the outer electron of Mg. So that is technically right, because this is they're in. It's this is going to be I suppose it's going to be 2s2, right? So 2s1 and 2s2, right? So okay, configurations 1s2, 2s2. So 1s2, 2s2, and then 2p. We don't have p. 2p. Sorry, I am having a brain freeze right now. 1s2. Wait, just a second. They're in the third period, and then they're electrons. 1s2, 2s2, 2p6, 3s1, 1s2, 2s2, 2p6, 3s2, right? So sodium, magnesium, they're the same orbital, yes, 3s1, 3s2. But that doesn't really explain the statement, does it? Like, why is the second ionization energy of sodium larger? Second ionization energy of magnesium, it doesn't really have anything to do with what they're talking about. Because we're talking about Na plus and Mg plus, so that doesn't really have any relation with what they're talking about. So D is wrong for that reason. Like, it's technically right, but it doesn't really make what it doesn't really answer what they're asking, so we're going to cross out D as well. So yeah, answer is then going to be A. The attraction between the nucleus and the outer electron is greater in Na plus than in Mg plus. Okay. Next question. Which graph correctly shows the relative melting points of the elements magnesium, Mg, Al, Si, and P plotted against the relative electronegativities? Okay, yeah, that reduce screen size. Okay. So, okay. Melting point. So melting point, silicon will have the highest melting point because it's in group four, and group four exists as giant structures, right? So I can, on that basis, I can cross out A and D because silicon must have the highest melting point. Okay. And phosphorus, because it's a non-metal, it will have the lowest melting point, whereas magnesium and aluminum are metal. So phosphorus will have the lowest, which is true for B and C, which are the options I'm considering now. Between aluminum and magnesium, aluminum will have the higher melting point because how because they exist in metallic lattices, right? Metals obviously exist in metallic lattices. So there's Mg2 plus, and it's sea of electrons, and then there are Al3 plus, then there's Al3 plus, and it's sea of electrons, right? So because Mg2 plus and Al3 plus, those are the most common um, ions, right? Like how they exist in their metallic lattices. So basically, each Mg atom loses two electrons, and then each Al atom loses three electrons. So basically, aluminium has more um, electrons in its conductivity band. Basically, it has a greater sea of electrons. There's more attraction between Al3 plus and its sea of electrons, stronger metallic bonding basically, and so it will have a higher melting point because of the stronger metallic bonding, right? In Al3 plus, in aluminium metallic lattice compared to magnesium's metallic lattice. So yeah, that's aluminium has a greater melting point than magnesium, which is the case in both B and C. So now we have to consider their electronegativities to compare whether like to see whether option B or option C is right. Right. So we see the periodic table. So we have magnesium, aluminum, silicon, phosphorus. Now across a period, it's similar trend to the ionization energy basically. That basically the electronegativities increase across the period. That's the general trend, and then yeah, they increase down the group. So why do they increase across the period? It's because the number of shells remains the same, so the atomic radius remains fairly same. Surely effect remains fairly the same, but the proton number is increasing, right? So proton number, because of the increase in proton number, what happens is that the nuclear force of attraction on the valence electrons increases. And again, it's the same logic as for ionization energy. Basically, um, yeah, the electronegativity increases across period. So that means that the highest electronegativity would be for phosphorus, the least would be for magnesium, right? According to what I said. And so here I should have phosphorus, but this is the opposite. I have phosphorus having the least electronegativity. That's such a hard word to say, actually. Now that I think about it, I should probably talk slower. Then it has the least electronegativity, and then magnesium has the greatest, which is wrong because, as I told you, the electronegativity increases across the period. So magnesium should have the least, which is the case in B, and phosphorus should have the most. And then aluminium will have more than silicon, obviously. So basically, the order is magnesium, aluminium, silicon, phosphorus. So it should be like this: Mg, Al, Si, P. That's the right order, which means option B must be the correct answer. Okay. So yeah, that's the answer, and I'm going to erase this scribbles. Okay, and let's go to the next question. Question 13. 13. Wait, I just did 13. Question 14. An excess of MgO is shaken with water. The resulting mixture is filtered into test tube X. An excess of BaO is shaken with water. The resulting mixture is filtered into test tube Y. Which oxide reacts more readily with water and which filtrate has a lower pH? Okay, lower pH means well, I mean MgO and BaO they form basic solutions, right? So then lower pH means it's less basic, basically, right? Anyways, let me write down the equations. So MgO is shaken with water. Okay, so that will give you MgO plus H2O gives you MgOH gas, I suppose. And yeah, that seems right. And then BaO plus H2O gives you BaO. So this is basically to do with basically the result. So this is in test tube X basically. and this is in test tube Y, right? But then you have to think that what's the trend down group 2 for the solubility of the group 2 hydroxide, right? So um, write down some of the group 2 hydroxides just in here because we're talking about magnesium barium, right? So I'm just considering these two right now. But basically down the group, the solubilities of the group 2 hydroxides increase, right? So they become more soluble in water, which means obviously if they're more soluble in water, then that means again there will be a greater number of Ba2 plus 2 OH minus OH minus ions present in the solution, or Mg2 plus OH minus, right? So if I compare these two, like the solubilities in water, so Mg2 plus MgOH twice aqueous and BaOH twice aqueous, right? So BaOH twice is more soluble in water, which means there will be a greater number of OH minus ions present in the solution because BaOH twice dissolves more, like it's dissolved more readily in water, or it's more soluble in water, right? So there are a greater number of OH minus ions present in the solution for BaOH twice, which is in test tube Y, right? So that means that it's this. That means that the solution will be more basic, right, or the filtrate, yeah. So it will be more basic because there are more OH minus ions present, so it will have a higher pH, right? So obviously the test tube Y will test tube Y's filtrate will have a higher pH. I am not talking very clearly today, am I? But anyways, MgOH twice is less soluble in water, so that means there will be less OH minus ions in the solution, and so it will have a lower pH, right? So that means that the answer is going to be that the test tube will filtrate of lower pH is basically this MgOH twice one, which is test tube X. So I'm going to take this A or C. And then which oxide reacts more readily with water? Again, I told you that BaOH twice is more soluble in water, right? That's trend down group 2, that they become more soluble in water, and good for the group 2 hydroxides. I mean. So that means which oxide reacts more readily with water? That's going to be barium. Okay, they're talking about oxide, sorry. Reacts, they didn't say is dissolved, right? I should have read the question more quickly. Oxide reacts more readily with water. Again, it's still going to be barium oxide, really, because now if you think about the sizes of the ions down group 2, so magnesium, imagine this is magnesium, and this is barium, right? So Ba2 plus will react more readily, basically. Larger, like Ba is larger than Mg, right? So Ba2 plus is basically um yeah, like the, it's less stable. Should I say, or should I say that bonding is not too bad, not really different, but Ba2 plus has a greater lower charge density. In fact, it's a bigger radius than Mg2 plus. So because Ba2 plus is a bigger ion, it has a lower charge density, so it will react more easily because BaO is a less stable compound, basically. So it will react more readily with water because BaO is a less stable, the lower lattice energy. So the lower lattice energy, which is more of an A topic, but basically, yeah, that's going to be not wait, not being sorry. I got two ticks on A, so A is going to be the answer. So hopefully that makes sense. Next question. Samples of magnesium carbonate MgCO3 are placed in crucibles R and S. The sample in crucible R is heated until there is no further loss in mass and then allowed to cool. Sample in crucible S is left unheated. The dilute hydrochloric acid is then added to both crucibles. On adding the dilute hydrochloric acid, which observations are correct? Okay. So MgCO3, we have MgCO3, and then in R, it's heated until there's no further, basically there's thermal decomposition taking place, right? So MgO plus CO2. And then you then react it, so I'm just writing this down for R. Then you react the, because there's no further loss in mass, right? So basically let the CO2 escape. And then you react the MgO with HCl, right? So you get MgCl2 plus H2O, I would suppose. Um, 2 HCl, 2 HCl, right? And then for S, we're just taking the MgCO3 itself and reacting it with HCl, and then that is going to give you MgCO2 plus H2O plus CO2. Right, it's balanced. This is 2HCl. Yeah, now it's balanced. Okay, so those are the equations that I have, and then the question is that which observations are correct. So R, does it have a gas produced or no gas produced? But for R, I got, I let the CO2 escape, and they're asking about the observations with the dilute hydrochloric acid. So this equation basically and this equation, right? So over here, I have MgCO2, which is aqueous, and H2O, which is liquid. So there's no gas really. So I'm going to say no gas produced. For S, I got MgCO2, which is again aqueous, H2, which is liquid, and CO2 is definitely gas. So a gas is produced, and so the answer is going to be C. Okay? So no gas produced for R, but then for S, there is a gas produced. Okay, next. Which statement about nitrogen or its compounds is correct? In the Haber process, the temperature is kept high to give a good equilibrium yield of ammonia. No, it's just to have a good rate of reaction. I mean, it's not really kept high. I mean, yeah, it's just more to give a good rate. Because if I write down the equations, it's N2 plus H2 gives you NH3, and then if I balance it, so 3H2 and then uh, 2NH3 here, so 2 is that balanced? 3 to the 6, 3 to the 6, yeah, it's balanced, right? So integrations, switch to gaseous, 2NH3 gaseous. Anyways, forward reaction here is exothermic, backward reaction is endothermic. So if you have a high temperature is going to prevent the backward reaction is endothermic, because then the basically it will absorb the excess heat, and so you will re-establish equilibrium. So high temperature favors the endothermic reaction to the backward reaction. So if you want to get a good equilibrium yield, then that means you have to lower the temperature. But if you lower the temperature, then the rate will be too less. So you have to increase the temperature. So yeah, basically A is wrong because we're talking about the yield. They're relating the high temperature to the equilibrium yield. Wrong. Next is nitrogen gas. Okay, so you're asking about nitrogen gas is unreactive because of a strong nitrogen-nitrogen double bond. Okay, that's wrong. It's not a double bond, it's a triple bond. It's a very strong bond, but it's a triple bond. So they said the wrong thing, which is wrong. And then nitrogen monoxide will react with carbon monoxide under suitable conditions. That is right. It's a very important reaction, right, in the catalytic converter. So that's going to be N2 plus CO2 as I remember, and it's going to be 1 by 2 N2. Yeah, this seems balanced to me. Okay, so this is definitely right. It's the catalytic converter reaction, right? Now the formula of ammonium sulfate is NH4SO4. No, that's wrong. It's actually because NH4 has a plus charge, right? And SO4 ion has a 2 minus charge. So then the charge of the compound is going to be NH4 twice SO4. So D is wrong. That means C is the correct answer, right? So yeah, next question. When concentrated sulfuric acid reacts with sodium iodide, the products include sulfur, iodine, hydrogen sulfide, and sulfur dioxide. Okay, so which statement is correct? Hydrogen sulfide is the product of a reduction reaction. That's right. It is a product of a reduction reaction because if you look at H2SO4, in H2SO4 you have this SO4 2 minus ion, right? So I'm just going to take that. And then oxygen has a fixed oxygen number of -2. 4 oxygen atoms. You don't know the oxidation state of sulfur, so I'm just going to take it as X. And the whole charge of the SO4 2 minus ion is -2. So then X is equal to -2 plus 8. So X is equal to plus 6. Over here, basically sulfur has an oxidation number of plus 6, right? Whereas if you look at H2S, so in H2S, you have hydrogen, which has a fixed oxidation state of +1. Then you have two atoms of hydrogen, 2 times +1. S I'm going to take as X, and the whole oxygen number of the compound, the overall charge is 0, right? So 0. And X is equal to -2. So here in H2S, you have -2, right? As the oxygen number or oxygen state of sulfur. And so if you compare +6 to -2, so from H2SO4, which is concentrated sulfuric acid, and then the hydrogen sulfide, so +6 to -2, you are, the oxidation number is decreasing, right? So if it's decreasing, And obviously that's reduction that's taking place. So hydrogen sulfide is a part of a reduction reaction. That is right. Okay. Now, next, iodide ions are stronger oxidizing agents than sulfate ions, which, has to be wrong because, the sulfate ions are able to oxidize the iodide ions. Like in NaI, you have I minus, right? And then I minus, it's becoming, as you mentioned, it's iodine, right? So I minus becomes I2. And I2, you have an oxidation state of 0 for the iodine. Then I minus, which is an NaI, you have an oxidation state of -1. From -1 to 0, that is an increase in oxidation number, which means oxidation, right? So if your iodide ions are becoming oxidized upon reaction with sulfuric acid, and that means sulfuric acid has the sulfate ion, right? So 4 2 minus. So that means that because the iodide ions are becoming oxidized, that means that they are weaker oxidizing agents than the sulfate ions because the sulfate ions are able to oxidize the iodide ions, right? So if the sulfate ions are able to oxidize the iodide ions, that means the sulfate ions are stronger oxidizing agents than the iodide ions. So the statement should basically be the other around. Okay. And the next option, sulfur atoms from the sulfuric acid are both oxidized and reduced. No, they're not. Because firstly, in the hydrogen sulfide, I already showed that it's -2. If you check out the product sulfur, sulfur is just S, or you could say SAH if you're a purist. But just sulfur. Sulfur, obviously, because it's pure elemental form, is going to be 0. Its oxidation state is going to be 0. So from +6 to 0, again, it's a decrease in oxidation number, which is again reduction. So even in from H2SO4 to H2S is like that's also a reduction reaction, and H2SO4 to S is also a reduction reaction. So in both cases, sulfur is being reduced. So sulfur atoms from the sulfuric acid are only reduced, not oxidized. Okay, and sulfur atoms from the sulfuric acid are oxidized. Again, I told you it's reduction, so we can immediately cross out to make sulfur dioxide. Right? So sulfur atoms from the sulfuric acid are oxidized to make sulfur dioxide. Okay, so that's another product, right? Sulfur dioxide. Again, in sulfur dioxide, you have oxygen has a fixed oxygen state of -2. The two atoms of oxygen make -4. To balance that, sulfur must have an oxidation state of +4. Again, +6 to +4 is a reduction reaction. Anyways, this is wrong, right? Sulfur atoms from the sulfuric acid are oxidized to make sulfur dioxide. No, it's like H2SO4 is like it's undergoing a reduction reaction because it is oxidizing the iodide ions. Okay, so basically B, C, and D are wrong, and A therefore must be the correct answer because hydrogen sulfide is the product of a reduction reaction. Okay, next question. A solution of sodium hydroxide reacts with 3 moles of chlorine under certain conditions. Okay, the reaction produces 5 moles of sodium chloride and 1 mole of X, the only other chlorine containing product. Okay, so basically, I can already tell the conditions are, it's like hot, concentrated, um, and OH because it's producing 6 moles in total of the chlorine things, right? So anyways, I'm going to write down the reaction. NaOH is 1 mole plus Cl2 is 3 moles. I already told you, gives you 5 NaCl. And again, as I told you, it's going to be NaClO3. You should know this because it's like a very common case study which you've probably studied during your AS. But yeah, it's going to be this. So it's because it's because the NaOH is hot and concentrated. Like you could say it's perhaps a 70 degrees Celsius temperature. So um, yeah, that this is the reaction that occurs, and you should know this because you've probably seen it many times before, I guess, during your studies. But yeah, it's NaClO3, so you can immediately say the answer is going to C. Okay, and yeah, that's it. Not much to say about that, I think. So the next question. Um, redox is balanced, right? 3.6, 6 and OH, right? That's yeah. Now it's balanced, I think. 3 plus 3 6. So yeah, it's balanced. Okay. Next question. Redox reactions are common in the chemistry of group 17. Which statement is correct? Br minus ions will reduce Cl2 but not I2. Cl2 will oxidize Br minus ions but not I minus ions. F2 is the weakest oxidizing agent out of chlorine, chlorine, bromine, iodine. I minus ions is the weakest reducing agent out of F minus, Cl minus, Br minus, I minus. Okay, so let me just write down the things somewhere. Use another color. This color looks pretty. So first I write down the elements of F2CO2, bromine, iodine, acetylene. Poor acetylene. Everyone forgets about acetylene. Okay, over here, okay, I'll write down the other ones as well, the ions. So fluoride, chloride, bromide, iodide, and acetate. And we look at the trends down both of them. So these elements, they this is how the elements the exist, right? Like fluorine exists as naturally, so and Cl2 exists naturally as chlorine exists naturally as Cl2. So all of these have an oxidation number of 0, right? And then here F minus, Cl minus, Br minus, you can see the charge is -1, right? So they have an oxidation number of -1. So 0, if you're going from F2 to F minus, from 0 to -1 basically, the oxidation number is decreasing, so it will be a reduction reaction, right? So if going from F2 to F minus is a reduction reaction, that means whenever F2 reacts to from F minus, it is acting as an oxidizing agent because it is itself being reduced, right? As you can see. So these are oxidizing agents, okay? And then if you look at the opposite thing, which is from F minus to F2 or Cl minus to Cl2, and you're going from -1 to 0, which is an increase in the oxidation number. If it's an increase in the oxidation number, that means it's oxidation, right? And since in that reaction of F minus to F2, fluoride is being oxidized, that means that it is itself acting as a reducing agent, right? So these, like the ions, fluoride, chloride, bromide, iodide, they're reducing agents. Now, if you look at the trend down them, these actually become weaker oxidizing agents of the group. You already know the fact that the reactivity of halogens decreases down the group, right? And as I told you already, the naturally exists as F2, CO2, Br2, I2. So you can associate that with the fact that because they're oxidizing agents, the reactivity of the halogens decreases down the group, which means basically they're also becoming weaker oxidizing agents down the group, right? The natural form of them. But then if you're thinking about the ions, it will be the opposite thing, that they actually become stronger reducing agents. The ions become stronger reducing agents than the fluoride, chloride, bromide, iodide, acetate. Okay, so those are the trends. Now let's analyze the options. Br minus ions will reduce Cl2 but not I2. I have Br minus, and it will reduce Cl2 but not I2. Okay, so let me think about this. So Br minus, like, again, they become stronger reducing agents down the group, right? So if I look at I minus versus Cl minus. So Br minus, Cl versus Cl minus. So Br minus is a stronger reducing agent than Cl minus. So it will be able to reduce Cl2. Yes, it will be able to reduce Cl2 to Cl minus. But if you think about I minus, so Br minus is a weaker reducing agent than I minus. So that means if you're reacting Br minus with I2, then I2 will be this reaction will not take place basically because I minus is a strong reducing agent for Br minus, so Br minus will not be able to reduce I2 to I minus basically. I hope I'm making sense, but basically that means that option A will be right. Okay, because Br minus is a stronger reducing agent than I minus, but a weaker reducing agent than Cl minus. So it's able to reduce Cl2, but it's not able to reduce I2. Okay. Next option, Cl2 will oxidize Br minus ions, but not I minus ions. You can different color, okay. Blue. Okay. Cl2 is here. Will oxidize Br minus ions, but not I minus ions. So Cl2 is a weaker oxidizing agent than both Br. So actually, it's a stronger oxidizing agent, I mean, than Br2 and I2, right? So stronger than both Br2 and I2, so it's able to oxidize both Br minus into Br2 and I minus into I2. So both reactions will be able to take place if you're using Cl2. So that means that the statement is wrong. Cl2 is able to oxidize both of these ions, right? So B is wrong. F2 is the weakest oxidizing agent out of fluorine, chlorine, bromine, iodine. See, they always forget aspartame. Poor aspartame. But no, as I showed you, the trend is that they become weaker oxidizing agents down the group, right? So F2 is actually the strongest one. So this is wrong. I minus ion are the weakest reducing agent out of fluoride, chloride, bromide, iodide. Again, as I told you, the trend is that they become stronger reducing agent of the group, the ions, the halide ions. So this will also be wrong because iodide ions out of these four, like fluoride, chloride, bromide, iodine, are actually the strongest reducing agents. So this is also wrong. And so the answer is going to be A because we already eliminated B, C, and D, and I showed you the logic for A. So yeah, so A is going to be the answer. Next, we have, I suppose, is it organic now? Structural isomerism and stereoisomerism should be considered when answering this question. Each of the following carbonyl compounds is reacted with NaBH4, which is a weak reducing agent. Okay, so it's not able to reduce carboxylic acids, for example. Okay, so weak reducing agent. The product of each reaction is heated with Al2O3 at 600 degrees Celsius, generating one product or a mixture of isomers. Okay, so basically, heating with Al2O3 at 600 degrees Celsius, that implies that it's going to be a reaction which is basically dehydration of alcohols, right? That's the elimination of water, basically call it, or dehydration of the alcohol, right? That's the reaction that taking place when you're reacting with Al2O3 at 600 degrees Celsius heat. But NaBH4 is a reducing reaction, a reduction reaction. Okay. So which carbonyl compound will produce the most isomers after these processes? Processes, whatever it is. Okay. So butanal. Butanal is basically 1, 2, 3, 4. That's a four-chain molecule, and then butanal is an aldehyde. So this is the thing. Okay, so that's how the works skeletal formula for butanal. And then butanal, when you first react it with NaBH4, NaBH4 is able to reduce butanal into butanol. Okay, so that's what you get. Then when you dehydrate this alcohol, when you're reacting with Al2O3 at 600 degrees Celsius, it's going to become an alkene, which is like this. Okay, so it loses OH from here, and from this carbon atom, it loses H. So you basically OH and H together, you've lost water basically. Okay, so you've lost water to form from the alcohol to form an alkane. Okay, so this is the alkene you get. Will this have any isomers? No, it will not because if I draw it out, CH3, CH2, CH double bond, CH2, right? So over here on this one, you have one CH attached and another. Let me erase that. Okay, this is a mess. So you have two of the same groups attached to the same carbon atom in this double bond, right? Here you have two atoms attached to this double bond, which means it will not be able to show geometrical isomerism. So it cannot have isomers, basically. Uh, and then if you can think about butanone, which is this is option A. Okay, now I'm different. It's basically it's just one isomer. But let me check out the other options. The butanone is going to be this thing. Then when you react it with NaBH4, the ketone is going to be reduced to secondary alcohol, so it's going to become like this. Then this one can actually form two alkenes, right? Because you could lose, we obviously lose this OH, but you would lose the H atom to form H2 from this carbon atom or this carbon atom, right? So basically you lose the H atom from an adjacent carbon atom to the carbon that has the OH, right? So I could either form this thing if I lose the H from here, this alkene, or if I lose the H from here, I will form this, okay? Which it doesn't look that pretty right now. Wait, let me draw the double bond a bit better. I'm never sure where to draw double bond lines, okay? It's going to come up, but anyways, that's the thing. Next, let me see if this has isomers. So the first one is the same as the one I got in A, right? So it doesn't have isomers. But the second one, it does have isomers. It has, this is the this is the trans form, and the cis form will be something like that, right? So this is the cis form, which is so the chair form, both form, right? So cis and trans. So it does have geometrical isomers basically, because it has two different groups attached to this carbon atom and two different groups attached to this carbon atom, right? So, so it will show trans. So basically, from this B compound, I have gotten three isomers. So I can immediately eliminate A because that gave me only one, whereas B gave me three. So for now, my answer is B, but let me check the other options. C. Okay, pentane 3-on, which is going to be this thing. Okay, now if I first react with the NaBH4, NaBH4 will reduce the ketone to a secondary alcohol, which is this one. And then we're going to get after the dehydration process with the Al2O3, we're going to get this. Let me just draw this double bond here. So it will become this, and or you could get it, you could lose it from this H atom or this atom, but basically you get the same thing because these two are the same molecule. So this is the same as this one, right? So I'll just, it's just one isomer from that. But now, if I consider does it have cis trans, it does have cis trans because this carbon atom has two different groups attached to it, one H atom and one CH3. And this one also has two different groups attached to it, one H atom and one C2H5, right? So basically, this can show cis trans. Okay, so do I want to draw it as cis trans? Let me. No, but if you could draw it as cis trans, suppose it would just be like this. Yeah. So we can write in the note, put it like that. So yeah, it doesn't look right. Right. Writer. That's writer. More right. So that is how I can write better with that looks better. No. I'm sorry for this, guys. I'm sorry. I wanted to draw this. Okay. So yeah, that's the molecule. And now basically I've gotten two isomers from this, right? So that's less than three again. So I'm going to eliminate this option as well. Now option D is my last option. Let me try propanone, which is this thing. Propanone will, when you first react with the secondary alcohol, sorry, not the secondary, so you react with NaBH4, you get a secondary alcohol, which is this. And then if you dehydrate that, you get this alkene or this alkene, which is the same thing. So yeah, and does that have any isomers? No, it doesn't. I mean, any geometrical or optical isomers. Um, I did consider geometric. Well, no, actually. This one cannot have any geometrical isomers. This one cannot have any geometrical isomers. This one cannot have. Okay, yes. No need to consider that. Sorry, not geometrical. I meant optical. Optical isomers. So option D does not have any optical or geometrical isomers because this carbon atom has two H groups attached to two H atoms attached to it. Same carbon atom, which means there can't be any cis trans isomers, right? So this thing just has one, and so the answer is just going to be B. Okay, so yeah, let's go to the next question. The drug cortisone has the formula shown. In addition to those chiral centers marked by an asterisk, how many other chiral centers are present in the cortisone group? So I don't have to count the ones that are already marked. Those will be count. Use a highlighter. Okay, so I have one here. This one, no one. Basically, a chiral center will basically be a carbon which has four different groups attached to it. So it has to have four groups attached to it, and those four groups attached to it. Okay, so I can't consider this because there's a double bond there. And how can I consider this? That's already marked. That's already marked. This is another one. Then this is another one. That's it. So how many is that? That is 1, 2, 3, which is the maximum option that they give. So yeah. Next, an alkene is reacted with acidified manganate 7 ions, MnO4 minus. Okay, and then the desired organic product has a relative molecular mass greater than that of the alkene by 34. 34. That means I could consider it because 16 is the relative atomic mass of oxygen, right? So 16 times 2 would be 32. So that means hydrogen is 1. That's just relative atomic mass. So that means 32 plus 1 plus 1 to 34. So I can assume that there are two oxygen atoms and two hydrogen atoms. So would it be OOH, HOOH? That doesn't make sense. So it's probably going to be MnO4 minus, right? So I could have a diol situation, so it could be OH, OH. So whatever conditions give me a diol, basically, would be the correct answer, in my opinion, because 16 plus 1 plus 16 plus 1 would be 34, which is how much the relative molecular mass greater by than that of the alkene by. So cold concentrated makes no sense. That's not what we use. Hot dilute again makes no sense. That's not what we use. Cold dilute is definitely the condition for a diol to form from the alkane. And then hot concentrated is the condition for the whole rupturing of the double bond, right? So that's what we need. As I told you, it's probably going to be a diol. So yeah, the answer is going to be then, right? That's the one that gives you a diol. Next. The diagram shows a short length of an addition polymer chain. Polymer has a relative molecular mass of approximately 10,000. Approximately how many monomer units are joined together in each polymer molecule? This is the monomer, right? So monomer is basically C, double bond C, H, 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 okay? So what is the MR of this thing? That's the two carbon atoms, so that's 12 times 2, and there are 4 of the hydrogens, so 1 times 4. If you calculate this out, it's 24 plus 4, so basically 8, not 8, sorry, 28. So 28 is the molar mass of the monomer. And since the total relative molecular mass of the polymer is approximately 10,000, so how many monomer units are there? It's going to be 10,000 divided by the molecular mass of one monomer, right? So 10,000 divided by 28 should give you the answer. 23, that is 357.14285. That's a cool number. And if you look at the options, it's closest to 360, it is option. Okay, B is going to be my answer. Okay, next question. Lactide is an intermediate in the manufacture of a synthetic fiber, that's cool, which compound on heating with an acid catalyst. On heating with an acid catalyst, heating and an acid catalyst. Okay, so that makes me think that they're talking about upon esterification basically. So which compound upon esterification basically can produce lactide? So now all the compounds that give me hydroxyethanoic acid, hydroxybutanoic acid, so these are all compounds that have COOH as well as OH. So this compound basically together will form. You don't need to add any additional alcohol or carboxylic acid thing. You just heat this compound with an acid catalyst and it produces it gets esterified itself, okay, with itself. So if I just see these ester bonds, right? So if I just break these ester bonds, what compound do I get? That's the compound that will give me lactide, right? If I break these ester bonds, OH, like I'm taking this molecule, okay? So OH means it highlighted using the highlighter thing. I'm taking this compound, right? Or you could take this side of it. So I'm taking the left side. Okay, so OH and this thing, and that, and over here, yeah, OH again. So this is the compound. If I look at this compound, how many carbons does it have in its main chain? It has one, two, what? What? 1, 2, 3. Okay, let me make it 3. So it has 3 carbon atoms in its main chain, so it has to be a propanoic acid. So I can eliminate A and B. Then I'm considering the I'm considering this as the starting one, right? So this is my because the COOH side will have the priority, right? So this is carbon 1, this is carbon 2, and this is carbon 3. Which is the OH is on carbon 2, right? So this is 2 hydroxy, which is 2 OH, exactly 2 hydroxy propanoic acid. So C has to be the correct answer. That this compound that I got here is 2 hydroxy propanoic acid. So when I and on this side as well, you have 2 hydroxypropanoic acid. So when you basically heat 2 hydroxypropanoic acid in acid catalyst, it reacts with another molecule of itself and produces lactide. Okay, so 2 hydroxypropanoic acid. The answer is going to be C. Next. Okay, next question. Diols in which both hydroxy groups are bonded to the same carbon atom spontaneously eliminate a molecule of water to produce a carbonyl compound. Which compound is hydrolyzed to form a product that gives a positive reaction with 2,4-DNPH, so it basically has a CO, carbonyl group, right? But not with Ferenc reagents. If it does not give a positive reaction with Ferenc reagent, that means not an aldehyde. So it's not an aldehyde. It's going to be a carbonyl compound, but not an aldehyde, which means ketone. So, we're talking about which compound is hydrolyzed to form a ketone, basically. Which compound is hydrolyzed to form a ketone, right? So now, diols in which both hydroxy groups are bond to the same carbon spontaneously eliminate a molecule of water to produce a carbon alcohol. Okay. So using this information, I will check which compound will be hydrolyzed to give a ketone. So option one is option A, I mean, is 1,1 dibromopropane, which is this propane. 1,1 dibromopropane means the bromine is here, and then both, specifically first, you have uh, it's hydrolyzed initially. So then you get an OH here and an OH here, right? And then uh, you know this will, like, when this molecule is formed, because they said that diols in which both hydrogen groups are blah 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 blah, spontaneously eliminates a water, right, molecule. So basically this will spontaneously eliminate a water molecule, I suppose it's about, I don't know at which period of time. Um, the arrow of interruption. Anyways, this will then become what do you call it, an aldehyde, right? Because they're on this first carbon atom, or end carbon atom. So it will give me a ketone with the carbonyl compound that will be produced from the elimination of a molecule of water will be an aldehyde. Since it's an aldehyde, A cannot be the correct answer because I need a ketone, right? So A is definitely not the answer. B, if I check the option, check B. B is 1,2 dibromopropane. This is bromine here, and they're right. So they're not on the same carbon atom, basically, which means I don't get this. This is as far as it goes. This spontaneous elimination of water to produce a carbonyl compound will not occur because they're not bonded to the same carbon atom. So that's it. So basically, B is also going to be wrong, right? And then now if you look at option C. Sorry, I'm a bit sick right now. 1,3 dimethylpropane. Again, the problem is like the same problem. They're attached to two different carbon atoms. So when it gets hydrolyzed to form this thing, it will not again spontaneously be eliminating water. So it's also wrong. So then the only option that's left is D, right? So D is going to be the correct answer. But again, we have to test out the option first. I mean, if you have time, obviously, if you already know what the answer is in an exam, you don't need to try it out. But I'm going to try it out because it's just a video, right? So I have time right now. So this is 2,2 dibromopropane, just like this. Then I will hydrolyze it to get the OH substitution, and then this will spontaneously, because you're bonded to the same carbon atom, so this will spontaneously eliminate the H2O to give you a carbonyl compound, which is actually a ketone. So F is going to be the answer. So ketone is the answer. So D is going to be the answer because it gives me, obviously, a ketone gives you positive test with for D and pH, but it will not give you positive test with phenylbutyrate, right? So basically, D is going to be the answer. And now we go to the next question. X and Y are the reagents required to convert 1-bromopropane into butanoic acid. Okay, what are the correct identities of X and Y? Okay, so firstly, we have this Br going in, like, turning into, or being substituted by Cn, because there's substitution, right? So this would be, it's just a nucleophilic substitution reaction. So the conditions for this are KCN or NaCN in ethanol, right? Ethanolic KCN in ketone reflux, obviously. So which option is that? NH3. Why would you do that? HCN, no, that's for nucleophilic addition. Uh, yeah, that doesn't make any sense. It's a haloalkane reaction. Nucleophilic substitution, so it should be KCN in ethanol, situation OH. Then Then we have Y. Reaction Y is that Cn is going to become COOH, which is basically acid hydrolysis. Because it's COOH, right? Not COFE. So COOH means that it's acid hydrolysis, so it's basically HCl aqueous, which is option A or C. We eliminate B and D because it has to be acid hydrolysis. Because it's not the salt, it's actually acid. COOH, COOH. And yeah, and then you heat and reflux as well, obviously. So then the answer is going to be C, because that's where we have two things, right? Next question, number 27. Q is a compound. The molecular formula C4H10O. Q can be oxidized with acidified reaction back with 6. Q cannot be made by reducing a carboxylic acid with LiAlH4. Okay, so if Q cannot be made by reducing a carboxylic acid with LiAlH4, I mean, obviously these are all alcohol options, right? So that means that Q is definitely an alcohol. Now, if this Q, which is an alcohol, cannot be made by reducing a carboxylic acid with NiH4, that eliminates the option that it's the possibility that it's a primary alcohol. Because primary alcohols, like when you reduce a carboxylic acid with NiH4, you get a primary alcohol, right? So that means that it cannot be Q cannot be a primary alcohol. So you can eliminate option D, which this is the primary alcohol, and we can eliminate option B, which is again a primary alcohol option. So it's either going to be A or C. Then the question, like the thing they're saying, is that Q can be oxidized with acidified potassium bicarbonate 6. And since it can be oxidized, that would suggest that the ones that the alcohols that can be oxidized are primary alcohols and secondary alcohols. Tertiary alcohols cannot be oxidized. If you look at option C, CH3 triCOH, that is a tertiary alcohol. So again, this is eliminated. So this is a primary alcohol, that's why it's eliminated. This is tertiary alcohol, that's why it's eliminated, because tertiary alcohols cannot be oxidized, but Q can be oxidized, right? So that means Q must be a what would happen secondary alcohol, and so A must be the correct answer because A is the only secondary alcohol option. If you want, I can draw it out and show you that it's secondary alcohol CHOH CH2 CH3, right? So this OH is attached to this carbon atom, and this carbon atom that the OH is attached to two other carbon atoms, and since it's attached to two other carbon atoms, it's a secondary atom, right? So yeah, that's the logic. And I'm going to erase this because I need space. Okay, yeah. Nice. A sample of 2.30 grams of ethanol was mixed with an excess of aqueous acidifying reaction by 6% CH3CH2OH, it's ethanol, and you are oxidizing it to give you excess aqueous reduction dichromatic, right? So that will give me CH3 CHO. That wait, no. It's excess aqueous and it's boiled under reflux. It give me CH3 COOH actually. So it give me ethanoic acid. So ethanoic acid, and then yeah. So now I'm not concerned about balancing the equation. Basically, the important thing is that 1 mole of CH2CH2OH is forming 1 mole of CH3COH. That's the important thing. It's 2.30 grams, and yeah, so the yield is 60.0%. So if I have 2.30 grams of this, how many moles do I have? What is the MR of CH3CH2OH? That would be 12 times 2 because there are two carbon atoms, plus 3, 4, 5, 6. So 6 hydrogens, so 1 times 6, and oxygen is just 16. So that would be 24. Plus 6 plus 16, which is 46. So it has a MR of 46 grams per mole. We'll erase this because again I don't have space. Sorry about that. Okay. This is 46.0 grams per mole. So what would be the moles? Moles would be mass over MR. So 2.30 over 46.0. 2.3 over 46. So that would be 0.0500 moles. Okay. So if this is 0.0500 moles, theoretically, if we 0.0500 moles, right? And so M equals to N times MR. Now, if we want to find the MR of CH3CO, it will be 12 times 2 because there are two carbon atoms, 24, plus 16 times 2 because there are two oxygen atoms. So that will be 32. Plus there are 4 hydrogen atoms, so 1 times 4 is 4. And so you get an MR of 16 grams per mole. Okay. Now M equals moles times mass equals moles times the molar mass, so N times MR. So that will be 0.0500 into 60. So that will just be 3.00 grams. So this is the theoretical yield, right? So then we have to actually find what mass of product was actually collected. So theoretically, you would have 3 grams collected, but actually as X. Okay. So then times by 100, the actual yield is 60%. Okay. So then, or you could say 60%. So you just say 60.0 over 100. Okay, so then you just have to find the value of X. So let me find the value of x. X is equals to 60 over 100 into 3, which is going to be 1.80 grams. So this is the actual yield, actual mass product, which is ethanoic acid. And so the answer is going to be C. Okay? Yeah. Okay, now next question. Which compound was a positive test with alkaline aqueous iodine? So it could be a methyl ketone or a secondary alcohol with adjacent um, methyl group, right? And does not show optical isomerism. Okay. So if I look at the first option, CH3CO, CH2, CH2OH, and draw that out, one, two, three carbon atoms, and then OH here, and CH3CO, right? So this. So is this a methyl ketone? It is a methyl ketone. So it would give you a positive test with alkaline aqueous iodine. Does it show optical isomerism? No, it does not. It does not have any carbons. So this could be the correct answer actually. So I think A is the correct answer, but obviously we check the other options as well. I mean, in the exam again, just to do the question as fast as you can. I have time right now, so one, two, three, four, then CHO, and then CHOH. Yeah. So um, this is not a methyl ketone, firstly. So that's the first check gone. Second check, which is does it show optical isomerism? Yes, it does, because this is a chiral carbon. So basically failed both the things, the requirements. So B is definitely out. Then if you look at option C, um, CH3CO has 1, 2, 3, 4 carbon atoms with this OH, and here is CH3CO, and this is optically active molecule, so that means it's immediately out, even though this is a methyl ketone. It will show a positive test with alkaline aqueous iodine, but because this carbon atom is, it shows optical isomerism, this is a compound shows optical isomerism, so this, because this is a carbon carbon, so that means this option is out. Next, we have this compound, 1, 2, 3, 4, CHO, and OH, right? So this is the compound. Does it, is it a methyl ketone? It's not a methyl ketone. It's not a methyl ketone. And it does not show optical isomerism, which is fine, but again, it's not a methyl ketone, so it's the option is out. It does not show optical isomerism because this carbon atom has two the same groups attached, like two CH3 groups attached, and this carbon atom has a double bond. Right? So this does not show optical isomerism, and it is not a methyl ketone. So, now next question. Citral is found in lemongrass oil. It can react to give compound W. What would compound W be? Okay, so an excess of H2Ni, that would mean that these bonds, you get a hydrogen added there. So hydrogen added, and it becomes this thing. I didn't draw it right. I will draw it again because I feel like I do it wrong. So this is like this, and then this is like this. This is that. And this, that, and then you have this. Yeah, that's how it looks. Okay, that's the molecule you get. CHO will not be reduced by H2 it's not produce carbon atoms. So then a concentrated acidified manganate 7 under reflux will be, that will basically um now this will oxidize the CHO, right? So this will become CO2H. Okay, so that is what happens. And now which product matches with what I got as W? Let me see. This is wrong. That's wrong. That's wrong. So B matches with what I got, right? So B must be the answer. Wait, just let me check. Actually, got one thing that can H2 reduce the aldehyde. Can H2 reduce hydrogen? Oh, Okay, so H2. Oh, simplest large-scale procedure for reduction of aldehydes and ketones to alcohols is by catalytic hydrogenation. So that can happen. So H2 can reduce aldehydes and ketones. So another correction here. So instead of this, it should actually be CH2OH then, I suppose. And then obviously still that will become less oxidizing to CO2H, so that doesn't change. That's not good. I get the point. So H2 can reduce hardness primary alcohols and ketones to secondary alcohol, but I don't think it can reduce carboxylic acids, right? I don't think it reduces carboxylic acids. See, after addition of H2, the unsaturated portion became saturated and the carboxylic acid remains unchanged. So it does not reduce carboxylic acids. So I don't know that's cool. So hydrogen and yeah, this hydrogen palladium or whatever can reduce aldehydes and ketones as well as these alkenes, but it cannot reduce carboxylic acids, from what I understood. If I am wrong, just correct me in the comments, but this is what I understood, okay? So yeah, this is just correction to be made that CH will become CH2OH and that will become CO2H when it's specified. Hot concentrated acidified manganese 7 under reflux, okay? So now we are done with these 30 questions and now we have section B. So let's do it. Okay, so beams of charged particles are deflected by an electric field. In identical conditions, the angle of reflection of a particle is proportional to its charge to mass ratio. Okay, so they're saying that means that the angle of deflection of a particle, let me take it as theta. Okay, so theta is directly proportional to charge to mass ratio. So let me take a charge as Q and mass as M. This is Q over M. So then basically that means that theta, let me introduce the constant, right? So this is just maths of how we do direct proportionality things, right? Theta equals KQ over M, then the constant K is going to be theta M over Q, right? So K is a constant, basically, right? Now, in an experiment, protons are deflected by an angle of plus 15. Okay, so protons are deflected by an angle of plus 15. Protons are basically one, oh, what happened to my screen? One B, right? So that's one charge. So, anyways, in another experiment under identical conditions, particle Y is deflected by an angle of minus 5 degrees. So, if it's deflected by an angle of minus 5 degrees, it's deflected in the opposite direction to the proton, which means that it probably has this particle Y probably has more electrons than protons. So if I look at these options, more electrons than protons, so one could be valid, two could be valid, but three has more protons than electrons, but then it would be then it would also be deflected positive in the positive direction, right? Like the proton, it's deflected in a negative direction, so it must have more electrons than protons. So I would say three is wrong. Now I'm not sure about whether both one and two are right yet, but I would say that would be a good guess. But I just want to confirm basically. So what I'll do is I have this thing right, k equals theta m by q. Theta is my angle of reflection, m is the mass of the particle, and q is the charge, right? So let me see if for both cases I get the same thing, right? For the proton, k, my constant k, like which is a constant, so it should be the same in all cases. Basically, the angle is plus 15, and then I'm not really converting from degrees to like radius or whatever. It's just okay. I'll just put like this, okay. And mass is going to be one u basically because the unit of mass will be unified atomic mass unit, which is u, and the unit of the charge will be element, like I'm taking it in terms of elementary charge, which is 1.60 into 10 to the power minus 90 coulombs, right? So protons charge will be plus 1 e, right? So that's the calculation for k, and so I get plus 15 U by E. So that's my constant K. Now, if I look at option one, I'll use different colors. It will be easier to see. I mean, by this point, you probably already know that the answer is going to be B, right? Because one and two are right. As I told you, there should be more electrons than protons. But I just want to check as well. Okay? So you can, if you want, you can do this check. Really, you don't have time on the paper, so this should be a pretty good guess because I don't think there's much more you can do that. Anyways, maybe it's more logical behind it. I don't know. So K equals now the for this particle Y, the mass number, which is so basically for firstly the deflection is -5, right? Deflection is -5, then m, the mass, is going to be the number of protons plus neutrons, which is 2 plus 1, 3, so times 3u. And then the charge will be, so I have two electrons and one proton, so the total charge will be -1, right? Overall charge. So -1 E. E is the elementary charge. So then minus and minus become plus, so it becomes plus 15 U by E, which is the same as I got this thing as, right? So basically, 1 is definitely a valid option, and I just confirmed it as, yeah, I confirmed it. Then if I go to 2, is it there again? So for 2, I have K equals to, again, it's -5 reflection. I told you that. And then times, now the total number of, the mass will be the number of protons plus neutrons, 3 plus 3 will be 6. So 6U. And then the, what do you call it? The total charge of the particle Y is, it has 5 electrons, that's -5, 3 protons, so plus 3, that becomes -2 E, right? So it's -2 E. So then minus becomes plus. 2 times 6 by 2 is 3, so 3 times 5 will be 15, so it becomes plus 15 U by E. That's just simplification. So yeah, again, it's the same constant that I got, plus 15 U by E. So B is also definitely a valid option. Now, if you look at C, C gives you K equals to -5 again as a deflection. And the mass is number of protons plus neutrons, 4 plus 5 is 9 times 9U divided by, now I have plus 4 for the protons, -1 for 1 electron, so plus 3. So plus 3E. So you can immediately see that minus times plus, minus divided by plus will be minus. So it's immediately going to be a wrong answer. And then 9 divided by 3 is 3. 3 times 5 is 15. So it will be -15 U by E. So it's definitely wrong because you get minus sign instead of plus, right? So 3 is wrong, so 1 and 2 are right, and B is going to be the answer, okay? So yeah, those 1 and 2 are right. Next, graphene, graphite, and fullerene C60 are allotropes of carbon, which statements are correct for all three of these allotropes of carbon. Delocalized electrons are present in the structure, that's right, because in all three of them, carbon is forming three bonds, and there's one uh, sort of delocalized electron in the p orbital. That's one, unpaired or it's just a delocalized electron, basically, yeah, because carbon is forming three bonds, three of them: graphene, graphite, and C60. And all bond angles are 120 degrees. That's true for graphene and graphite because, again, as I told you, they're forming three bonds, and there's one. It's just like that, not a bonding electron. Um, But so in graphene and graphite is basically you keep having those things. I mean, it's just this is a hexagon, right? So these all these bond angles are 120 degrees between the C carbon atoms is all 120 degrees. But in C60 fullerene we have pentagons as well as hexagons. So let me see if I can draw a pentagon properly. I cannot. Well, I can probably. I just didn't try that hard. 1, 2, 3, 4, 5. So in a pentagon, what would happen is that how in math you calculate the exterior angle using 360 by n, so that will be 360 by 5, which is going to be 72 degrees, right? So my interior angle, which is this angle, will be 180 degrees minus 72 degrees. Sorry for the math. I'm just showing you what the angle will actually be. So it's around 108 degrees, I suppose, or 109. But yeah, so basically fullerene C60 has pentagons and hexagons in the structure, right? Pentagons, hexagons, just both of them. So it would have bond angles ranging from 108 or 109 to 120 degrees, basically. So basically, what I'm trying to say is that all bond angles are 120 degrees is not true for fullerene, which is true for graphene and graphite. Now, As for you can see a picture of fluorine on the internet, by the way, if you want to see. Anyways, number three, kind of like a footballer. Question option number three. It has a giant molecular shape lattice structure. Okay, so again, that's true for graphite and graphite. They are giant molecular crystalline lattice things, but it's not true for fullerene because fullerene, you can see the number of carbon atoms is limited. It's limited to 60 carbon atoms. Since it's limited, it's not a giant structures. It's limited, right? It's limited to a finite number, which is 60, and you know, because of that, it's basically a nanoparticle. It's a nanoparticle, and this option is wrong. Basically, option three is wrong. Option two is wrong. Only option one is right. Since only option one is right, the correct answer is D. Okay. Next question. A reaction between carbon and oxygen is shown. Right. Um, so how can the enthalpy change of this reaction be described correctly? Okay. Enthalpy change of formation. So, well, standard enthalpy change of formation is the enthalpy change under standard conditions when one mole of a compound, and this is one mole of a compound. Well, actually, no, I'm talking about this, right? It's one mole of formation. So this one mole of a compound is formed from its elements that exist in the standard state. So carbon solid, O2 gaseous, so they exist in the standard states, and you're forming one mole of CO, which is this. It could definitely be enthalpy change of formation, yes. Now, enthalpy change of combustion is the enthalpy change under standard conditions when one mole of a substance is burnt in excess of oxygen to form combustion products, various combustion products. And so I have one mole of carbon, yes, but it's not excess of oxygen. You're getting carbon monoxide. It's not reacting in like excess of oxygen to give you CO2. If it was excess of oxygen, it would be CO2, right? So that means that it's not really an efficient of combustion because efficient of combustion requires the thing to be burnt in excess of oxygen. So it's not an efficient of combustion. An enthalpy change of atomization, the standard condition of atomization would be the enthalpy change in standard conditions when one mole of gaseous atoms is formed from its element that exists in standard physical state. So really, this is it's not really one gaseous atom, right? It's just a pretty it's really a compound, right? So one mole of gaseous atoms. So I would say that this is wrong for that reason, and I can cancel this option out as well. So then my answer is just going to be that one is right, so that means the answer is D. Okay. Next, which changes can be used to measure the rates of chemical reactions? The decrease in concentration of a reactant per unit time. Yeah, that's definitely true. The rate of appearance of a product. Again, that's also definitely true. The increase in total volume per unit time at constant pressure. That's also true. I mean, if there's a gas produced or something, then that you collect it, and then you can see how much gas is produced due to collective to unit time, blah blah blah. So all three are right. So I'm going to say that the answer is A. All right. Now, next we have question number 35. Which statements describe a trend in period 3 between every pair of adjacent elements from sodium to chlorine? So, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Okay, so they ignored argon. Poor argon. From sodium to chlorine. So every pair of adjacent elements could be sodium, magnesium, magnesium, aluminium, aluminium, silicon, silicon, phosphorus, phosphorus, sulfur, and sulfur chlorine. And we're ignoring argon. So yeah, the atomic radius decreases. That is right because along across the period, if you see over here, across the period the number of protons is increasing, right? So if the number of shells remain the same, so if the number of shells is remaining the same, then shielding effect is fairly the same, and but the proton number is increasing. So because the proton number is increasing, the nuclear charge is increasing. Because of that, the nuclear force of attraction on the valence electrons increases, and so then the valence shell gets pulled in slightly across the period as we go across the period. So atomic radius does decrease. Yes, and the ionization energy decreases. No, because as I told you right now, atomic radius decreases slightly, and again, as I told you right now, the nuclear charge increases across the period, right? And because the nuclear charge increases, the nuclear force of attraction on the valence electrons increases across the period, and because of that, it becomes harder to lose the valence electron across the period. So that's why the first ionization energy increases, and again it increases. because it takes more energy to, you know, ionize the thing possibly. So that means that 2 is wrong. The melting point decreases. Now again, I said there's a pair between every pair, right? Every pair. So that's wrong. Melting point does not decrease in every pair. Because sodium and magnesium, for example, if you look at it. So sodium is, sodium, magnesium, aluminum, they have, what do you call it? Metallic lattices, right? So they exist as metallic lattices because they're metals. So sodium, it exists as Na plus and a sea of electrons. Magnesium exists as Mg2 plus and a sea of electrons. Aluminum exists Al3 plus and a sea of electrons. So sodium, it becomes Na plus in its metallic lattice, right? So it will have it will have lost one electron per every sodium ion, whereas magnesium will have lost two electrons per every magnesium ion, and so magnesium has more electrons in its conductivity band than sodium, and just like that, aluminum has more electrons in its conductivity band than magnesium, and because of that, aluminum will have the strongest metallic bonding between Al3 plus and a sea of electrons. Because of that strongest metallic bonding compared to sodium and magnesium, it has the greatest melting point out of those three. And so the melting point is increasing from sodium to magnesium and from magnesium to aluminum. Then it's also increasing from aluminum to silicon because silicon is in group 4, so it exists as a giant lattice, right? So a giant structure. So, a giant structure, silicon, the element. I mean. So yeah, again it increases, and then obviously from silicon to phosphorus it will decrease because then it becomes non-metal. So basically, my point is that the trend between every pair of innocent elements is not that the melting point decreases because here it's increasing, here it's increasing, here it's increasing, and there it's decreasing because we obviously the case is for before I say CO2, right? So 2 and 3 are wrong. One is the only correct option here. So D is going to be the answer. Okay. Now next we have question number 36. X is either nitrogen or sulfur and forms polyvinyl oxide Y in a car engine. Further oxidation of Y to Z occurs in the atmosphere. In this further oxidation, 1 mole of Y reacts with zero point 0.5 moles of gaseous oxygen molecules. Which statements about X, Y, and Z can be correct? Okay, so let me write down the equations. Firstly, we have sulfur plus oxygen, giving you sulfur dioxide. This is X, this is Y, and then sulfur dioxide is reacting with oxygen to give you sulfur trioxide, which is Z. This is Y, and this is going to be run by 2, right? So that's a set of equations for sulfur. Now for nitrogen, we have N2 plus O2 gives you NO, so that's half O2. And then NO plus O2 will give you NO2, so this will be half O2. So this is X, this is Y, this is again Y, this is C. Okay, so now these are the equations. Now, is this statement right? In this further oxidation, 1 mole of Y reaction 0.5 moles of gaseous oxygen molecules. Let me see. This is 1 mole, this is 0.5, right? That's right. And then over here is volume 1 and 0.5. So this statement is right. Okay, so it can basically, why did I check that actually? We stated that already, but anyways, whatever. Now, which statements about X, Y, and Z can be correct? The oxidation number of X increases by 2 from Y to Z. Okay, so over here, oxygen is a fixed oxidation state of -2. -2 times 2, because there are 2 oxygen atoms, become -4. Balance of sulfur has to be +4. And similarly, in sulfur dioxide, -2 times 3 will become -6. So to balance that, sulfur has to be +6. So +4 to +6 is an increase in oxidation state by +2. So it's right for sulfur. Now for nitrogen, oxygen is -2, so nitrogen must be +2 to balance it. Then here oxygen is -2 times 2 because there are 2 oxygen atoms, -4. So then nitrogen has to be +4 to balance that. So +2 to +4 is again an increase in oxygen number by +2. So that means again it's valid as well for nitrogen. So statement 1 is definitely right. Now statement 2, Y has an unpaired electron in its molecule. Um, so let's check out sulfur dioxide. So SO, right? That's why. Now it has this lone pair of electrons, and One, two, one, two. So it has no unpaired electrons. It has lone pairs but not unpaired. So it's not true for sulfur dioxide, but you have to know that it said X is either nitrogen or sulfur. So if it's not true for one, it could be true for the other, and then statement two would be valid. So if I check out nitrogen oxide, it looks something like this, right, like that. And then it has one unpaired electron here as well, right? So one, two, three. I mean one lone pair as well. Yeah. So um, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, but I think that's how it's supposed to be at least. Maybe I didn't draw it exactly right, but this is how I think it's supposed to be drawn. I need to check on that. But it does seem to have one unpaired electron in its molecules. I would say that two is right because nitrogen monoxide does seem to have unpaired electron. Let me just see. Let me just see. Yeah, it does seem to be right. That's the same thing I drew, except yeah, why did they do that? 1, 2, 3, 4, 5, 6. They only drew one bond. I suppose that is also, but then you see, you could draw it like that, I suppose as well. But then this is also another image I found, which is double bonded. I like that double bond thing properly, so I'll just keep it like that. So double bond, double bond. Yeah, that's for NO minus. This is for NO. So yeah, that seems to match with my structure, so I'll take it as a valid structure again with this one. My point is that it has a lone pair. So yeah. And then third statement is that Y is a polar molecule. If I check my SO2 and my NO, so over here SO2 will be destroyed. But better. Okay. So the thing about SO2 is that firstly, there how many what's the steric number? So it has two sigma bonds and one lone pair, right? I'm talking about sulfur, so OSO bond and lone pair. So basically the steric number is three because there's two sigma bonds and one lone pair. And so since it's three, that means that you would predict it to be a trigonal planar shape, right? So basically, the bond angle you would predict it to be 120 degrees. But then because of the lone pair, it gets reduced by 2.5. So instead of 120, it's more like 117.5 degrees. And basically, what you would call this is like a bent molecule. Okay, since it's bent, yeah, it's basically bent. So basically, this oxygen is partially negative, sulfur is partially positive, oxygen again is partially negative. So you would have two dipole moments here. Now again, it's the same thing you do in vectors. So I just resolve this like this kind of. Okay, and if you kind of have studied maths or physics, you would understand what I'm doing. But basically, these two kind of cancel out. Okay, these two cancel out because they're in opposite directions. But then this one and this one, these two downwards components, they add up, right? So because of that, you do have an overall dipole moment, and because you have an overall dipole moment, it is obviously a polar molecule. So SO2, my point is that SO2 is polar. So again, because it says either nitrogen or sulfur, I would already immediately state that three is the correct statement. But again, I will obviously, you can check for NO as well. Now again, there's a good electronegativity difference between nitrogen and oxygen. You can check that using Pauling electronegativity variable. I think they give you now. Now you don't have it at all. But maybe in this syllabus, it's there. Yeah. So nitrogen and oxygen, the difference is 3.5 and 3.0, so that's 0.5. So definitely, yeah, there is negativity difference. Okay. So yeah, basically there's a dipole moment like this because partially negative, partially positive, right? So oxygen is more electronegative than nitrogen. Oxygen is more electronegative than nitrogen. So that's why that would be the dipole is like that. So that's why it is a polar molecule. This we see. So yeah, it's polar. So yeah, all three statements are right. So the answer is going to be A. Okay. Okay. Next question. P and Q are a pair of cis-trans isomers. What must be the same for P and Q? So they're cis-trans isomers. So their empirical formula, yeah, it must be the same. Obviously, their functional groups, obviously, they must be the same. Because they're the same molecular formula, structural formula, but they have different, spatial arrangements. Skeletal formula is different. Like for example, in butene, it's like this for the cis form. Then for the trans form, this is the thing, right? So this is the chair form, and this is the boat form. So cis trans. Their skeletal formulae are different from the formula. So different. Actually, one and two are the only correct options here, and so the answer is going to be B. Okay, B. Now next, following statements are about the reaction of NaOH aqueous with three chloroalkanes shown. Which statements are correct? So okay, so CH3, CH3 twice, CH2Cl reacts to NaOH by an SN2 mechanism. Okay, so this is a primary halogenoalkane, right? The primary halogenoalkanes, yeah, they do react by SN2 mechanism because they don't have any stable carbon intermediate. They just go through the transition state, so it's a one-step mechanism. So it's definitely SN2, and I would say statement one is correct. Statement two: tertiary chloroalkane reacts more quickly than the others because the carbon atom bonded to the Cl atom is more positive in this molecule. Tertiary chloroalkane, yeah, tertiary chloroalkane means that will it react more quickly? No, it will react more slowly because it's a tertiary chloroalkane. That means it forms a very stable carbocation intermediate, right? So it will react by SN1 mechanism, and SN1 mechanism is the slow mechanism. I mean, it's slower than SN2 because it forms the intermediate, and it will be proceed by two steps, right? So this is wrong. Basically, it will react more slowly than the others. Right now, next, the third statement is the Cl atoms in the three chloroalkanes are attacked by OH minus. That's wrong because actually what happens is that um, the OH minus attacks the carbon atom, right? In the carbocation, or just the carbon in general for the consider for the transition state as well for the primary haloalkane. But basically, it attacks the carbon atom bonded to the Cl, not uh, the Cl. Actually, the carbon atom that is or was bonded to the Cl, not Cl. So yeah, anyways, the answer is D because only option one is correct. Okay, so yeah. Now, question number 39. For which reactions are the color changes described correctly? Pentanal plus hot acidified potassium bicarbonate. Okay, so pentanal is this thing, right? So it's aldehyde, 5 carbon chain aldehyde. So, color change will be orange to green with hot acidified potassium bicarbonate 6. Will there be a reaction? Yes, there will be a reaction. Because this can be oxidized into uh, this thing, right? COOH, it can be oxidized into pentanoic acid, which will give you again color change to orange to green. Now for number two, pentane 2-one, which is this thing. But actually it's not this thing. Wrong. Pentane 2-one would be this thing, right? Yeah, that's more like it. So ketone, which is one second carbon, and we have the carbonyl plus warm Fehling's reagent. There should be no change. That is right because warm Fehling's reagent will only give you a color change if there was an aldehyde. There will be color change from blue to red, but here you don't have an aldehyde, so it's a ketone, so there will be no color change. That's right. Now for cyclohexane is this thing, and then 4-5 potassium manganate 7 computer colorless. That is wrong because cyclohexane cannot be oxidized really because what do you do with this thing? You can't oxidize it is my point. Okay, so at least with gold, sorry, yeah, you can't oxidize. Okay, so gold is my potassium. So that's wrong. So statement three is wrong, and since statement one and two are the only ones that are correct, the answer is going to be B. Okay, so yeah, it's B. And then next, we have the last question. Which statements about ethanol and ethanoic acid are correct? Ethanol is this thing, and then ethanoic acid is that's not right. Should probably do that right. That's it's ethanoic acid. Okay. Both react with a suitable reagent to form an ester. That is definitely true. If ethanol reacts with a carboxylic acid, it will form an ester. If ethanoic acid reacts with an alcohol, it will form an ester, and obviously need heat and H2SO4, concentrated H2SO4 gases, right? Both react with sodium, that's right, because both of them have this OH group, right? So, COH, yeah, so yeah, both of them will react with sodium. Definitely, both are soluble in water, That is also true because both of them can form hydrogen bonds with water because of this OH group, right? So yeah, both of them can form or CO2 is OH. So they can both form hydrogen bonds with water. So they are both quite soluble in water. And so one, two, and three are all right. And because of that, your answer is going to be A. Okay. So now we're done with this paper. It was a good paper, but I got sick while I was doing the paper, so yeah, that's yeah. So it was very running right now. Anyways, it was nice. So thank you for watching, and have a nice day. All the best for your exam.